A tree is a data structure that simulates a hierarchical relationship among elements. Unlike linear structures such as arrays or linked lists, trees are nonlinear data structures that organize data in a branching format. Each element in a tree is called a node, with the topmost node known as the root. The root is connected to other nodes through edges, representing parent-child relationships. The root node is the starting point of the tree, and each node can have 0 or more child nodes. Nodes with no children are called leaf nodes. A tree also cannot have cycles. For example, an edge like this is not allowed. The tree also has a height, which is the number of edges between the root node and the lowest leaf node. In this case, since all leaf nodes are at the same level, the height would be 3. This example tree is a binary tree, which is one of the most common types of trees in computer science, where each node has at most 2 children, called the left and right child. The specific type of binary tree that is the subject of this video is a binary search tree. In a binary search tree, the value of every node in the left subtree of a given node must be less than the value of that node, and the value of every node in the right subtree must be greater. This rule must hold true for all nodes in the tree, ensuring that the binary search tree property is consistent across the entire structure. This property can be beneficial for efficiently searching, deleting, and inserting elements. Before we get into the operations, it's important to understand the concept of a balanced tree and how it impacts the tree's height. A balanced tree is one where the height difference between the left and right subtrees of every node is at most 1. If any node has subtrees where this difference is more than 1, the tree becomes unbalanced. This tree is an example of a balanced tree because every subtree of any node has equal height. Now, if we remove some of these leaf nodes, the tree will still be balanced because the height difference between the subtrees is still no more than 1. However, if we remove these specific nodes, the height difference becomes more than 1, making the tree unbalanced. In the worst-case scenario, a completely unbalanced tree will look like this, skewed or even zigzagging, resulting in inefficient operations. Now, let's calculate the height of a completely balanced binary tree, assuming the total number of nodes is n. At the first level, there is only the root node. At the second level, there are 2 nodes. At the third level, 4 nodes, and so on, up to 2 to the power h, where h is the height of the tree. If we sum up all these nodes, we get a total of n nodes. If you know a little bit of mathematics, you can solve for h, which turns out to be log n. However, in the worst-case scenario, if the tree is completely unbalanced, the height becomes comparable to the total number of nodes, n. As the tree goes from balanced to unbalanced, the height increases from log n to n. This change in height directly impacts the efficiency of operations, making them slower as the tree becomes more unbalanced. To implement this tree, we'll start by creating a node class. In the constructor, we'll take the key as an input parameter. Then we'll initialize 3 members. Left, this will point to the left child node of the current node, initially set to none. Right, this will point to the right child node of the current node, also initially set to none. Val, this member will store the value of the node, which is assigned to the key provided during the node's creation. Next, we'll initialize the binary search tree, or BST class. In the constructor, we'll initialize the root of the tree, which will be set to none initially, indicating that the tree is empty. After that, we'll define the operations that can be performed on the tree, such as insertion, searching, and deletion. Let's first start with the search operation in our binary search tree class. This is the public method that initiates the search operation. It takes the key we want to find as an argument and calls the internal helper method _search, starting the search from the root of the tree. This is the internal recursive method that does the actual searching. It takes the current node and the key as arguments. First, we have the base case. If the current node is none, it means we've reached a point where the key can't be found in the tree, so the method returns false. Then, the other base case. If the value of the current node matches the key, it means we've found the key in the tree, so the method returns true. If the key is less than the value of the current node, it means the key, if it exists, must be in the left subtree. The method then recursively calls _search on the left child of the current node. If the key is greater than the value of the current node, the method recursively calls _search on the right child, as the key must be in the right subtree if it exists. This might not be entirely clear through explanation alone, so let's visualize it to understand the process better. To search for an element, such as 4, in a binary search tree using recursion, the algorithm starts at the root node and utilizes the recursion stack to manage function calls. It first compares the target value with the current node's value. The target is less than the current value node, so it recursively searches the left subtree. If the target is greater, it searches the right subtree. Each recursive call is pushed onto the stack. And when the target is found, the function returns true. As the recursion unwinds, each function call returns true, propagating this result up through the stack. The final result, true, indicates that the target value exists in the tree. The time complexity of searching for an element in a binary search tree is proportional to the height of the tree, as this determines the number of recursive searches required. Similarly, the space complexity is proportional to the height of the tree due to the space needed to store function calls in the recursion stack. In a balanced tree, the height is logarithmic relative to the number of nodes, so both time and space complexities are big O of log n. However, in the worst-case scenario where the tree is unbalanced, the height of the tree is comparable to the number of nodes, leading to both time and space complexities degrading to big O of n. That was the recursive approach. The same thing can also be done in an iterative manner. To search for a key in a binary search tree, BST, using an iterative approach, you start by defining a search method that takes the key as a parameter. Initialize a variable current and set it to the root node of the tree. Use a while loop that continues until current is none. Inside the loop, check if the key is equal to the value of the current node. If it is, return true, indicating that the key is found. If the key is less than the current value, move current to its left child node. Otherwise, move current to its right child node. After the loop ends, if the key is not found, return false. Let's visualize the iterative search for the value 4. First, the algorithm checks the root element's value. The root's value is greater than 4. The algorithm moves to the left child in the next iteration. It checks the value again. It's still greater than 4. It continues moving left. Now that the current node's value is less than 4, the algorithm shifts to the right child. Once the match is found, the loop breaks and returns true. The time complexity remains the same as before, proportional to the height of the tree. However, the space complexity is improved to constant time, as the iterative approach only requires space for a few variables, unlike the recursive approach which needs additional space to store function calls on the stack. The next operation to consider is insertion. Let's first explore the recursive approach. First, we define the insert method. This method begins by checking if the tree's root is none. If the root is none, it means the tree is empty, so we create a new node with the given key and set it as the root. If the root already exists, the insert method calls a helper function, _insert, passing the root node and the key to be inserted. The _insert method is responsible for finding the correct position for the new key. If the key is less than the current node's value, the algorithm checks if the left child of the current node is none. If it is none, it means the correct position for the new key has been found, so a new node with the key is created and set as the left child. If the left child is not none, the underscore insert method is called recursively on the left child to continue searching for the correct position. If the key is greater than the current node's value, the process is similar but occurs on the right side. The algorithm checks if the right child is none. If it is, a new node with the key is created and set as the right child. If not, the underscore insert method is called recursively on the right child to continue the search. Else, if the value to be inserted is already present, the algorithm just returns. Next, let's visualize this process. Imagine we're inserting the value 11 into the tree. The algorithm will begin at the root node and compare the value 11 with the root's value. Since 11 is greater than the root's value, the recursion will move to the right child. Now this node's value is greater than 11, so the algorithm will move to the left child. The left child's value is also greater than 11, so the algorithm will move to the left again. At this point, the left child is empty, so the algorithm will assign the left child to a new node with the value 11, and then the recursion will return. The time and space complexity for the insertion operation are the same as for the search operation. Both are proportional to the height of the tree. The same operation can also be implemented iteratively. First, we'll start by defining the insert method. In this method, if the tree is empty, we'll create a new root node with the key value. If the tree already has nodes, we will initialize a variable called current and set it to the root of the tree. Then, we enter a while loop that will run indefinitely until we find the correct spot for the new node. Inside the loop, we compare the key value with the current node's value. If the key is less than the current node's value, we check if there is a left child. If there isn't, we create a new node with the key value and assign it as the left child. If there is a left child, we move the current pointer to the left child and continue the comparison. Similarly, if the key is greater than the current node's value, we check the right child. If the right child is empty, we create a new node with the key value and assign it as the right child. If there is a right child, we move the current pointer to the right child and continue the comparison. Finally, if the key equals the current node's value, we simply return without inserting a duplicate. This ensures that the new node is placed in the correct position in the tree while maintaining the binary search tree's properties. Now let's visualize inserting the value 11 using the iterative method. The process begins by creating a current variable, initially set to the root node. The algorithm will then traverse the tree by comparing the value 11 with the values of each node it encounters. Since 11 is greater than the root node's value, it moves to the right child. Then, as 11 is less than the next node's value, it moves to the left. Finally, it reaches a node with an empty left child, where it inserts the new node with the value 11. The time complexity here is proportional to the height of the tree, just like the recursive approach, as the algorithm needs to traverse from the root to the target position. However, the space complexity is constant, because unlike the recursive method, the iterative version doesn't require additional memory for function calls, just a few pointers to keep track of the current node during traversal. This makes the iterative approach more memory efficient in some cases. Before moving on to the delete operation, it's important to understand the min-value node function. This function is crucial when deleting nodes, particularly when dealing with nodes that have two children. The min-value node function takes a node as an input parameter and aims to find the node with the minimum value in a given subtree. It starts by creating a current variable, initially set to the input node. Then it enters a while loop, which continues as long as the current dot left is not none. Inside the loop, the current variable gets updated to the left child of the current node. This process effectively traverses the left side of the tree, and since the smallest value in a binary search tree is always the leftmost node, the function returns the leftmost node of the subtree. Let's break down how the delete method works in multiple steps. The process begins with the delete function, which takes the key to be deleted and calls the helper function _delete node, starting from the root node of the tree. The goal is to traverse the tree and locate the node containing the key. If the node is none, it means the key does not exist in the tree, and the function simply returns none, stopping further execution. If the key is smaller than the current node's value, the algorithm continues searching in the left subtree. It calls _delete node recursively on the left child, setting node.left to the result. On the other hand, if the key is greater than the current node's value, the search moves to the right subtree, where the function is similarly called on the right child by setting node.right to the result. This ensures the algorithm finds the node containing the key. Once the key is found, the deletion occurs, which varies depending on the structure of the node. If the node to be deleted has no left child, it returns the right child, essentially replacing the node with its right subtree. If the node has no right child, it returns the left child, removing the node and replacing it with its left subtree. For the case where the node to be deleted has two children, the algorithm needs to find the in-order successor, which is the smallest node in the right subtree. It uses the helper function, _min_value node, to find this smallest node. The current node's value is updated to the successor's value, and then the algorithm deletes the in-order successor from the right subtree to avoid having duplicate values in the tree. This maintains the binary search tree property, ensuring all nodes to the left are smaller and all nodes to the right are larger. Finally, the function returns the updated node, maintaining the tree structure even after the deletion. This approach guarantees that the binary search tree remains valid and balanced after a node is removed. Let's visualize the delete operation with animations. Suppose we need to delete the node with the value 11. The algorithm will begin at the root node and compare the key with the current node's value. It will recursively traverse through the tree, moving either left or right, depending on whether the target value is smaller or larger than the current node. In this case, the target element 11 is a leaf node, meaning it has no children. Once the algorithm finds the node, it will simply remove it by setting the parent node's reference to none. Since it's a leaf node, there's no need to restructure the tree further, and the recursion will return, confirming the deletion. The tree will be updated with 11 removed, maintaining the overall structure. Now, let's visualize deleting the node with the value 12. The algorithm will start at the root and, as usual, traverse the tree by recursively comparing the target value with the current node, moving left or right based on whether the target is smaller or larger. In this case, the node with the value 12 has one child. Upon reaching the target node, the algorithm will not simply delete it as in the case of a leaf node. Instead, it will update the parent node's pointer to point to the child of the node being deleted. This effectively bypasses the deleted node and connects its parent to its only child, maintaining the tree's structure. The recursion will then return, finalizing the deletion process. Now, let's add some nodes and try to delete a node that has two children. We'll go with deleting the node with the value 5. The algorithm will first traverse to the target node recursively. Upon reaching the node with the value 5, it will identify that this node has two children. To handle this, the algorithm will use the _min_value node function we defined earlier. It will start by looking at the right child of the target node and iteratively find the smallest value node in the right subtree. Once the smallest node is found, the algorithm will update the value of the target node to this smallest node's value. Finally, it will proceed to delete the smallest node, which will either be a leaf or have at most one child, simplifying the deletion process. Once the smallest node is removed, the recursion will return, and the deletion operation is complete. For one last example, let's delete the root node. The algorithm will begin at the root, which is also the target element for deletion. Since the root has two children, the algorithm will need to find the smallest node in the right subtree, following the same process as before. Once the smallest node is located, its value will replace the value of the root node. Next, the algorithm will proceed to delete the smallest node from the right subtree. In this case, the smallest node has one child, so the algorithm will update the pointer of its parent node to point directly to the smallest node's child, effectively removing the smallest node from the tree. This completes the deletion process, with the root node's value replaced and the tree structure updated accordingly. The time and space complexity for this recursive approach is proportional to the height of the tree, which depends on whether the tree is balanced or not. Now let's see the iterative delete method. This method uses a loop to delete a node with a given key from the binary search tree while maintaining the tree's structure. The process involves several steps depending on the position of the node and how many children it has. The method starts by setting two variables: current, which starts at the root of the tree, and parent, initially set to none. These variables help track the node we are trying to delete and its parent during the traversal. First, the algorithm searches for the node with the key to be deleted. It uses a while loop to traverse the tree. The parent variable is set to the current. If the key is smaller than the current node's value, it moves to the left child. If the key is larger than the current node's value, it moves to the right child. If the current is none, it returns none. Once the node is found, the method handles three possible cases. Case 1. The node has no children, meaning it's a leaf node. In this case, if the node is the root of the tree is set to none, making the tree empty. If the node is a left child of its parent, the parent's left reference is set to none. If the node is a right child of its parent, the parent's right reference is set to none. Case 2. The node has one child. This could either be a left child or a right child. If the node only has a right child, the method bypasses the node and links the parent directly to the node's right child. If the node only has a left child, the method links the parent directly to the left child. This effectively removes the node while preserving the connection to its child. Case 3. The node has two children. In this case, we need to find the smallest node in the right subtree, known as the in-order successor. We do this using the _min_value node method. The value of the in-order successor is stored, then we recursively delete the successor node. After that, the value of the node to be deleted is replaced with the value of the successor. This ensures that the tree remains a valid binary search tree. Now, imagine deleting the node with the value 12 from this tree. The algorithm will first iteratively traverse the tree to find the target node, which is 12. Once the target is found, the algorithm will evaluate the cases to determine how to proceed with the deletion. In this case, the node 12 has a single child, which is 13. The parent of 12 will then be directly connected to 13, bypassing 12. This effectively removes 12 from the tree while keeping the child node in place. The time complexity in this case is also proportional to the height of the tree. However, the space complexity is now constant, because the iterative method only requires a fixed amount of memory to store a few pointers, such as current and parent, during traversal. Now let's move on to the operation of getting the height of the tree. In this case, we'll only focus on the recursive approach, as it is typically done using recursion. Here's how it works. First, the public function will be called, which serves as an entry point. This function doesn't do any computation itself. Instead, it calls the helper function, passing the root node as the input parameter. Then inside the helper function, the algorithm will check if the current node is none, which means we've reached the end of a branch, so the height at this point is 0. Then it will recursively calculate the height of the left and right subtrees. The function will continue this process until it reaches the leaf nodes, and for each node, it will return the maximum of the left and right subtree heights plus 1. This ensures that the height of the tree is properly calculated by comparing the depth of each branch. This process will eventually return the overall height of the tree. The algorithm for calculating the height of the tree starts at the root node. From there, it recursively traverses the left subtree first. It continues to move left until it reaches a leaf node. Upon reaching a leaf node, the base case of the recursion is triggered, and the function returns 0, indicating the height of a leaf node. After returning from the left leaf node, the algorithm moves to the right unvisited node. If this is also a leaf node, it again returns 0. At this point, the algorithm is back at the parent node, and it calculates the height by taking the maximum of the left and right subtree heights, which are both 0. Adding 1 for the current node, the function returns a height of 1 for this subtree. The same steps are followed as the function moves up the tree, calculating the height for each node. For every node, the maximum of the left and right subtree heights is taken, and 1 is added to account for the current node. Once the algorithm finishes calculating the height of the left subtree, it moves to the right subtree and follows the same recursive steps. It traverses down the right subtree, reaching the leaf nodes, and returns 0 upon hitting the base case. For each node in the right subtree, the algorithm calculates the height by taking the maximum of the left and right subtree heights and adding 1 for the current node. This process continues recursively until the algorithm has traversed and calculated the height for all nodes in the right subtree. Finally, when both the left and right subtree heights are known, the algorithm returns to the root node and computes the overall height of the tree by taking the maximum of the left and right subtree heights and adding 1. This gives the total height of the entire tree. In this case, the time complexity would be big O of n, since it traverses the entire tree. However, the space complexity of this operation is still proportional to the height of the tree because the recursion stack only holds information about the current path from the root to a leaf node at any given time. This path's length is equal to the height of the tree, not the total number of nodes. Let's talk about traversing the tree. In this code, the public preorder function first calls the inner underscore preorder function, taking the root node as the input parameter. The print statement at the end of the public function is there to create a new line after the traversal completes, ensuring clean output formatting. Now, inside the helper function, the first step is to check for the base case. If the node is none, meaning we've reached the end of a branch, the function will return and stop further execution. If the node is not none, the function will print the value of the current node to represent visiting that node. Recursively, move to the left subtree, calling on the left child. After the left subtree is fully traversed, it will recursively move to the right subtree, calling the function on the right child. This method ensures that each node is visited in preorder, node first, then left, then right. Let's see this visually. First, the algorithm will start at the root node and print its value. Then, it will recursively traverse down the left subtree, printing the values of the left child nodes as it visits them in preorder, node first, then left child, followed by right child. Once it has fully explored the left side of the tree, the algorithm will backtrack and move to the right subtree, following the same preorder process by visiting and printing the right child nodes. This ensures that the traversal visits nodes in a root, left, right sequence, covering all nodes in the tree. Next is the in-order traversal, which is similar to the previous pre-order traversal, except that it first traverses the left subtree before visiting the current node. In this method, the algorithm will first recursively explore the left side of the tree until it reaches the leftmost node, then it will print the value of the node. After printing, the algorithm will move to the right subtree, following the same pattern. This traversal follows the left, root, right order, ensuring that the nodes are visited in ascending order. Let's see this visually. The algorithm will start at the root node and will recursively traverse the left subtree until it reaches the leftmost node. At this leftmost node, it will print the node's value. After printing, it will then move to the right node of the current node and continue this process. The algorithm ensures that all nodes are visited in the left, root, right order, printing the values in ascending order. Next is the post-order traversal. In this method, the algorithm first recursively explores the left subtree of the tree until it reaches the leftmost node. It then proceeds to print the value of the leftmost node. After finishing with the left subtree, the algorithm moves to the right subtree of the current node and follows the same process, recursively traversing the right subtree until reaching the rightmost node and printing its value. This traversal follows the left-right root order, ensuring that the nodes are visited after both their left and right subtrees have been fully explored. Let's see this visually. The algorithm starts at the root node and first recursively traverses the left subtree until it reaches the leftmost node. At this leftmost node, it prints the node's value. After printing the leftmost node, it then backtracks to the parent node and moves to the right subtree, repeating the process, traversing recursively to the rightmost node and printing its value. Finally, after exploring both left and right subtrees, the algorithm prints the value of the current node. This ensures that all nodes are visited in the left-right root order, with values printed in post-order traversal. For all three traversal methods, pre-order, in-order, and post-order, the time complexity is big O of n, where n is the number of nodes in the tree. The space complexity for these recursive methods depends on the height of the tree. For recursive call stack,